Hello, my name is Luan Guedes Costa, and today I'm going to show you a work entitled Chaos and Hyperchaos in a 2-degree of freedom Duffing oscillator. This work was done by me, by Professor Luciana Monteiro and Professor Marcelo Salvo. First of all, I'm going to talk about the introduction, about Duffing oscillators, its applications, and the motivation behind this work. After that, the mathematical formulation, the physical modeling, and the stability analysis. Then the numerical simulations, the conclusions, and the future work after that. The Duffing oscillators are basically classical nonlinear second order ODE present in the literature that exhibits complex phenomena as bistability and chaos. It is often used to represent some mechanical and electrical nonlinear systems. Also, is used in some emergent research fields as encryption for messages and energy harvesting systems. So it is versatile, has many applications. It has a wide literature exploring single-degree freedom systems, but has a few texts exploring multiple degree freedom systems. And you can see also in the literature a continuous effort to map and quantify dynamical behaviors of these kinds of systems to find the best configurations for different kinds of applications. So, to the physical modeling, consider the mechanical representation here, that you have two nonlinear elements attached to two masses, and a long process of substitution that you can access in the full text here. Just scan the QR codes. That results in this dimensionless equation of motion of the system. Here in purple are the forcing parameter. Here in blue are the damping terms. And here in red are the restitution force parameters. For that nonlinear elements here. So also the stability analysis shows the emergence of 16 possible equilibrium configurations. For this work, we chose one, the most complex one, that has these parameters here. And if you consider also the potential energy function of the system, you can show in a graph in this subspace, the equilibrium points of the system. So in blue here, you have the stable ones, 4 stable, and the unstable ones in red. Also, you can see the wells here, for the stable equilibrium points, and the valleys here for the unstable equilibrium points. Also, it's important to name these stable equilibrium points, as it will be important in the future analysis. Now, the dynamical analysis, considering these parameters, and especially those that characterize a domain of parameters, and these ones that are the initial conditions of the system that are based on the EP6, that is one of these stable equilibrium positions here. Also, the tools we use for analyze the dynamics of the system, that is the fourth order Runge-Kutta integrator, the Poincare maps, and Lyapunov exponents to map and identify different kinds of dynamical responses. So here are the results. As you can see here, in this big graph, you have a diagram for dynamical attractors. Here in the color legends, you can see gray is period 1 attractors, yellow is period 2 attractors, and so on, and until it reaches in blue, that is period 6 attractors until quasi-periodic attractors. Then you have in red chaotic attractors, and in dark red, hyperchaotic attractors. So in this graph, you can see the predominance of period 1 responses and hyperchaotic responses. Also, you can find specific zones of 32, 33, 36 or more, and chaotic as well. And it's very difficult to find period 4 and period 5 attractors. Period 5 here, you can see you have a small cloud of points, and period 4 here, here, and here, maybe. You can see it's hard to distinguish without a zoom. So also below you can see diagrams for the largest Lyapunov exponents and the second Lyapunov exponents. Basically, these values were used to classify chaotic and hyperchaotic attractors. Positive Lyapunov exponents are in color, and negative Lyapunov exponents are in grayscale colors. Basically, if you have just one positive Lyapunov exponent, the largest one, you have chaotic motion. If you have the two of them, lambda 1, lambda 2, you have positive, you have hyperchaotic motion. If you analyze more this diagram, you can see that increasing the frequency, you have an increasing magnitude of the positive Lyapunov exponents. Then it reaches a point that it rapidly decreases. The same goes here, happens here. So now let's consider those two regions marked here, in which when gamma changes, lambdas also rapidly decreases. So let's take a look in the first one here. We have a hyperchaotic attractor here. When the second Lyapunov exponent rapidly decreases to negative, it changes to chaotic motion, and then the first one also rapidly decreases to negative and then turning into periodic motion. Now let's analyze some phase subspaces of these diagrams. The first point is a steady state period 1 orbit that oscillates around EP9. Look that the initial condition of the system is in EP6, and then it changes in steady state to EP9. A similar behavior occurs at this point here, this period 2 orbit, and this period 3 orbit. Also occurs at this period 4 orbit, but take a look at these numbers here. As I said before, it's really hard to find this kind of attractor in this domain we are analyzing. So imagine if this is hard to find in numerical experiments, imagining real experiments. It's not an easy task. So the same thing I can say about the period 5 orbits, but in spite of that, look that this is oscillating around multiple equilibrium positions. So basically around EP8, this central unstable position, and this EP7. Here we have another interesting behavior, a multiple periodic orbits oscillating around EP9. A star-like attractor, but it's not chaotic because of the values of the exponents. And we have here an example of a chaotic attractor that is oscillating around all but the central unstable equilibrium position. And here we have an example of a hyperchaotic orbit that oscillates around all equilibrium positions. So another interesting thing to observe is that the difference between the chaotic attractors and the hyperchaotic attractors, because the chaotic attractors are more fractal-like structures, and the hyperchaotic attractors are more messy structures, don't have a form like the chaotic ones. So the conclusions, the principal objectives of this work was to map and identify dynamical patterns, especially the chaotic and hyperchaotic responses. Stability analysis shows 16 possible configurations but we choose only one, the most complex one. And the dynamic analysis shows the predominance of period 1 and hyperchaotic attractors. Shows also some robust small regions of period 2, period 3, period 6 or more in chaotic attractors. And it also show frail regions of period 4 and period 5 zones. For the future work, we'll do the dynamical analysis with different initial conditions based on the stable equilibrium points. The dynamical analysis of other equilibrium configurations of those 16, and also experimental verification. So thank you very much. This was my presentation. If you want to know more about this work, you can access here the QR code. You go straight to my ResearchGate page profile. So thank you very much.